In this presentation I'm going to be doing an introduction to differentiation, which is one of the two branches of calculus. In engineering we make use of differentiation a great deal. It's a very useful tool, very useful in engineering, very useful in physics and science, so it's used extensively. And hopefully as I go through it and explain what it's used for and what it is, that will become more obvious and you'll see why we use it so much. So on to the history. Now the history of calculus probably goes back well over 2,000 years, probably back to the times of Archimedes. So a lot of historians credit Archimedes with being one of the first discoverers of the process of doing calculus. What he did in his example was he used a form of calculus, a form of integration, to work out the area of a circle. But generally the history books give the credit to these two gentlemen here, Gottfried Leibniz and Isaac Newton. And if you want to look up anything on the history of that, you can do. There's a lot of videos on YouTube and you can go and have a look. They are both credited with discovering it about the same time. There was a lot of bad blood between the two guys, the two men, and you can go and watch YouTube videos on that and get drawn in and involved and post loads of comments and write some books about it and maybe find a new angle on it. But basically it wasn't a good part of history between these two people. Isaac Newton tended to fall out with people who he saw as a threat to him, his own glory, I guess, if I'm honest about it. I suppose that's what makes for being a genius. Anyway, so the credit goes to these two guys, and history is now recording that both people independently of one another discovered it. There was some overlap between them in the communications that sort of fueled the discovery, but really they both were geniuses in their own right, and they didn't just obviously discover calculus. Both of them had their own other discoveries. Isaac Newton probably the most famous for his discoveries. So what is it and why? Well, the why of it I'm not going to go into just yet. That will develop as I go through this presentation, and hopefully that'll I'll be able to get that message over. But let's have a look at what is it. Quite simply put, what is it? It's about finding the gradients. So if we've got a slope, as we've got here with this line, it's about finding what gradient is that. Now with a straight line it's quite easy, and you're probably familiar with this formula here. Y equals mx plus c. If you're not familiar with that, it's a very common formula. Basically what it's saying is that this m here is to do with the gradients, so that's how steep this line is. Common phrase we use is rise over run, and so as it runs along it rises up, so we say rise over run. And this here c is to do with where it crosses the y-axis. So it could actually be 0. If it went from this point down here along upwards, then it would be a plus 0. And of course it can be a negative as well. It could be down here, given as a negative gradient. Not a negative gradient, a negative c where it crosses the y-axis. You can have a negative gradient as well. It can go this way, it can go downhill, and that would be called a negative gradient. This one, as you can see, is a positive. So that's the background of what it's doing. So that doesn't answer the question though, what do we use it for? So let's have a look. So if I go to this next slide, in this we see more of an example of what it's used for. And then this is something that we're all familiar with but may not be immediately aware of. So we've got meters here and we've got seconds. So if you've got something, if you travel meters in so many seconds, what you've got there is speed. You may be more familiar with the phrase miles per hour, kilometers per hour. Obviously you wouldn't, 6 kilometers in 3 hours would be pretty slow. 6 kilometers in 3 hours would be even slower. But anyway, meters per second is the SI unit for velocity or speed, but velocity is the correct term that we use. So from this we can work out what our gradient is, and that will give us what the velocity is. So generally the way we do it is we find the gradient. You'll notice this one, by the way, has no c on it. It's passing through at 0, so we're not travelling at any speed, and time 0. Then we set off. In 3 seconds we get up to the speed of 6 meters. Okay, so from this we can work out the velocity. 3 seconds we've done 6 meters. So we'd do rise over run. So we'd find it from m equals, so we've got the rise is 6 minus 0, and the run is 3 minus 0. It's always nice if you can start these at 0 here. Quite often what you may do is choose a couple of points on the line. Doesn't matter where you choose them, it doesn't matter how far apart they are, other than the fact it can be a bit more accurate with the maths. So generally would say try to use distant points, but if you can include one of them to be 0, it makes the maths a lot easier. So basically what we end up with 6 over 3. So that would give us an answer of 2. Okay, so that'd be 2 meters per second. So I'll write it like that. You can write it like this. Okay, 2 meters per second, but we tend to like to write like this with a -1. Excuse me. Okay, so that would give you the gradient quite easily. Nothing difficult about that. Now the beauty of that is that's a nice straight line. So the speed is constant. It's 2 meters per second. So as you travel along, every second you've covered 2 meters. So when you get to 3 meters, 3 seconds, you've done 6 meters, and so on and so forth. So, and that you could calculate that for any length of time, how far you've travelled with that speed. That's nice and easy. Now, what about a more real-world example? So obviously, if you get in your car, you set off driving. You're not going to do a constant speed. You put it into gear and then you set off. So you're doing 0. Your speed increases. Your distance you travel. You're not doing a constant speed. Then your engine, if you're using an internal combustion engine, your engine will start to reach its maximum in that gear. So you'll have to change gear, whether it be an automatic gear change or whether you do it manually with a clutch. You've got to change gear. Then you can. So your speed starts to trail off, and then you change gear and it starts to pick up again, and then you've got your maximum power points and all these things where your power's at a maximum, so your speed increases the most. So it's not linear, in other words, is what I'm getting at there. So if we take a look at this one, if we've got y equals x squared, and I'm not saying that would represent the change in distance travelled with speed, with the car or the bike or anything, but it could be. Let's for argument's sake say it is. How would we find the gradient at any point in time? So if this is time along here, okay, and this is along here, there's our distance travelled, our displacement, we call it S, displacement, how far we travelled. As you can see, it's changing all the time. It wouldn't take the shape of, but let's say it would, for the argument's sake. How would I calculate the gradient along this point at anywhere along it? What we could do is we could choose a point. Say we want to find the speed here, at this point in time. So how would I find that? Well, what I could do is I could put a line of best fit on, put a tangent on, so something like that maybe. So now I've got a straight line. So I could do my rise over run, take these 2 points here, over here. Let me get the pen back on. So I've got my 2 points here. So I've got a rise over run. So I could cast these points down and across and calculate what they are and get an answer. That's nice, it works, it would work. A bit messy, you've got to draw yourself a graph every time, you've got to put your line of best fit on and then do your bit of maths. Now obviously the problem with that is if somebody else comes along and puts their line of best fit on, so they may get, for example, this. Okay, that's obviously way out, but you see my point, you see the argument I'm making, that different people will get different results, so they get different gradients. So what we need is a more precise method. Now this is where Isaac Newton and Leibniz came into their own, did a bit of thinking about it, and they thought of this. Instead of putting a tangent on, why don't we put what they call a chord on? So you select 2 points, join them together with a line and use that as a gradient. Now obviously that is a poor gradient for this point P here. Whoops. I would say it'd be something more like that, but it should be touching, but more like that. And they've got this, so you can see that gradient there and this gradient are miles apart. Okay, fair enough. What about though if we move P this way? It's a terrible arrow, but we move it up this way. So obviously as we move up, that line's going to get closer and closer. That's good, fair enough, but still miles out. What happens if we keep moving up though? Closer and closer, and closer and closer and closer. What about if, without touching it, but we get exceptionally close, really close? So basically you'd have to zoom in and then move it closer, zoom in a bit more and get closer, zoom in a bit more and get closer. This is what Isaac Newton and Leibniz did. And what they did here, so as you get closer, so you've got this y, so you've got your variation in y, so you've got this is basically your y2 plus y1, or your y1 plus y2 to be more precise actually. This delta symbol here, this is the Greek letter delta, okay, is used in maths quite often to mean a very small thing. It's a very small distance or a very small part of. So we're going to use a very small part of y. So we've got y and then we've got the distance removed from it, which is very small. So we've got this and we've got the change in x. So we've got our y there. We're going to eventually divide by this. Our x is y plus a very small distance and it's all squared. I'm not going to labour this maths. This is just so you understand where it comes from. If you want to go through this, go through it by all means, and as you'll see it will work out, but I'm not going to labour it. I'll just go through it very quickly, multiply it out, expand it out, y equals x squared, so I can remove the y and I can remove the x squared, so this leaves me with this term, multiply through by the small change in x, gives me this, cancel out, gives me this, so I end up with this phrase here. Okay, or this is the way we prefer to write it. So this is actually the differentiation, the rise over the run of y, of this phrase, y equals x squared. It gives me 2x. Okay, so that's from first principles. The derivative, we call it the derivative when you find the gradients, the expression for finding the gradients of some formula, as in this we've got here, y equals x squared. So the derivative is 2x. Okay, so it turns out that the gradient can be found from this expression at any point. So what I mean by that is, if I want to know what the gradient is at 1 second, if we're working in seconds, this is your x-axis. So if I say x equals 1, I'm not sure whether it would fall on here, but I would just put 1 in there, so it'd be 2 times 1. So the gradient at that point would simply be 2 times 1. So it would be 2. So the gradient would be 2. If I want to know what it is when x is 2, it'd be 2 times 2. So it'd be 4. Okay, what about 3? Same thing. So now I've got a means of finding the gradient at any point. Obviously 2 times 3 is 6. As you can see, it's getting steeper and steeper as we go along, which is agreeing with what we'd expect of this function, y equals x squared. Okay, nice and easy. Well, not really, because we've done it this is from first principles. But as it turns out, if I show you these results here, if we did this from first principles, if y equaled x squared, we would end up with this as a result, x 2x. So same again, well, you've seen that already. If I put in a value for x, this is derivative, dy dx, put a value in for here, it'll give me the gradient at any value of x, or, you know, any value of x, 1 billion, and 10 billion, and so on. This one, if I look at this one here, the derivative of this one is 3x squared. If I take this one, the derivative is 4x to the 3. Can you spot the pattern there? If you have spotted it, well done. Give yourself a pat on the back there. What we do, the shortcut way, so it saves us doing it from first principles every time, is you just take the power down to the front, multiply it in. So there's a number in front of here. We haven't written it, but there's a number, then it's a 1. So I've taken the 3 down, multiplied the 1, I get 3x. Then I've gone to my power, I've taken 1 from the power. So I've now got 3x to the power 2. And you see the same principle here, 4 down to the front, multiply it in, take 1 from the power. Dead simple. So that's a nice easy way. So all you got to do is remember that. Take the power to the front, multiply it into what's ever at the front, if anything. Well, there's always something, there's a 1 at least. Take 1 from the power. Nice and easy. What happens if there's a number there? Well, it's the same principle. We just multiply it in. So if you see here, 2 down to the front, multiply it in and we get 14. Take 1 from the 2, leaves me 14x to the 1. Same with this one, take the 3 down to the front, multiply it in, 21, 3 sevens is 21, take 1 from the power, I've got 2. What could be easier? Not much. So if you can do basic multiplication, you can take 1 away from a number, you've got it licked. Okay, nice and easy. Let's have a look at this one. What happens if the power is a negative number? Makes no difference, it's just the same, it's just basic maths. Minus 2 multiply 7, so that's straightforward. We've got minus 14 x. Here's a tricky, this is the hardest bit. What's minus 2 minus 1? No, it's not minus 1. If any of you said that, it's minus 3. Okay, this one got a minus sign out front, multiplied by a minus sign, a minus times a minus gives us a plus. I'll put that in to emphasize that. So 14, and again x minus 3. So it's easy, nothing hard about that. I trust you find that easy. I hope you do. Okay, let's have a look at another one. This one's looks hard, and if you're just thinking at this moment in time, I'm going to give this up, I'm going to give this calculus up, I can't do this, how's anybody expected to do that? Do it with it. The calculus part is easier, the hard bit is the maths part. So you've got to remember your laws of indices, or also known as laws of exponentials, if you use that phrase, also known as power rules. Okay, so what we're going to do, well, we can't do it as it is, so we've got to change it. Now, hopefully you know that x, square root of x can be rewritten as this. X to the power of a half. Okay, now we can deal with it. Still scared of it? Well, it's not, it's easy. You just multiply the half down to the front. If it's an easier way of thinking of it, change a half to a 0.5, then it probably looks a bit easier. So the dy over the dx of this, very simple. Bring the half down to the front. I'll bring it out front literally like that. X, and then take 1 whole from 1 half. So that's 2 halves from 1 half. From a plus half, that's going to give me a negative half. Okay, nice and easy. I could rewrite it like this. Same difference actually. So hopefully you didn't find anything difficult about that. Of course, if there'd been a number in front, you'd be multiplying it by a half. Say there was a 2 there, you'd be multiplying it by a half, so it'd just become a 1. If there was a 4 there, you'd be multiplying it by a half, so it would become a 2, and so on. Okay, so that's easy enough. Okay, now it's your turn. So in a few seconds, pause this video and have a go at these and see how you get on. Fingers crossed you'll get them all straight off pretty easily. Then start the video and I'll go through them. Okay, welcome back. So hopefully they didn't cause any problems. Let's have a look. Let's see what we can do. So the first one you should have found easy because I've already actually done this in an example. Let me just talk a little bit about this terminology. dy dx. Why are we using this? Well, what we're saying is we've got this d here is representing a change, small change in y. It's been divided by a small change in x. So that is our rise over our run in effect, but a very small amount, basically to make it correct. If you tried to do it like we did previously with a long line, you would become very quickly become inaccurate. But by doing it by this method, it's just an expression of a way of demonstrating what the gradient is, the rise over the run, but a very small rise divided by a very small run, basically tending towards 0, getting towards 0, but never quite getting to 0. So it makes it accurate, mathematically speaking. Okay, right, so what have we got? So the 2 comes down to the front, multiplies it into the 1 that's there that we haven't written, but it's there. 2x. Take 1 away from the 2, we've got a 1, becomes 1, which we tend not to bother writing, so we end up with this, 2x. So the next one, exactly the same process. So this one, the 2 comes down to the front, multiplies into the 3, so we've got 6x. Take 1 away again, so it's just to the 1, or you can just leave it as it is. So that one's easy. Next one, dy dx equals, so bring the 5 down, 3 times 5, nothing difficult about that, 15x. Take 1 away from 5 is 4. Easy again. This one, a little bit trickier, because this time we've got a negative number. 3 multiplied by minus 2, not that hard, is it? Minus 6 x, and then take 1 away from minus 2, and no, it's not minus 1, it's minus 3. That might be one of those, oh yeah, I forgot moments. So pretty straightforward. So hopefully you've managed to do them without any difficulties and you've managed to get through them all. Nothing hard on that, so hopefully this next slide's not offensive to you and you're thinking, yep, that was easy. Actually, some children are cleverer than some of us adults, but we never mind. In the next video I'm going to do, the next presentation, I'm going to have a look at some other functions. So far we've looked at what they call polynomials, so your x to some power, possibly with a coefficient in front. On the next one I'm going to look at the trig functions, so that's your sine and your cosine functions. They're not difficult, frankly. We'll have a look at those, and we'll also have a look at the log function, which will be natural logs, and I'll explain that when we come to it. And we'll look at the exponential function, the e, which is the base of natural logs, and again I'll explain that a little bit further when we come to it. Okay, thank you for listening.